In this video, we are going to talk about the there exists quantifier. So we've already seen in our last video the for all quantifier. So this symbol right here represented for all x such that p of x happens. Okay, so now I want to have a way of expressing the phrase there exists. Okay, so here is our definition. When we talk about the proposition there exists an x in the domain such that p of x is true, or I could also say that as there is an x in the domain such that p of x is true, I will denote the there exists with this symbol, which kind of looks like a backwards E, or kind of like a 3. So I write that symbol and then x, and then I write p of x. And the way I say this in words is there exists x such that p of x. Okay, so this backwards E looking symbol means there exists. And this is what's called the existential quantifier, because it talks about the existence of some x. So again, just to talk about the two quantifiers we have so far, that this ex means there exists an x in the domain such that whatever comes after it. And this symbol right here, remember, this meant for all x. For all x in the domain, and then whatever comes after that. Okay, so let's do an example where we use this. So I'm going to let m of x be 2x plus 3 equals 29, and I want to evaluate the truth value of there exists x m of x. And in part A, I'm going to let the domain be 10, 11, and 12. So for a there exists statement, for it to be true, I need to find one value, at least one value in the domain that when I, plug it into this equation, it's going to make it true. There could be more than one. As long as there is at least one that works, it's going to make it true. But if none of them work, if none of them, when I plug them in, make it work, then it's going to be false. Okay, so let's consider this. So because my domain here is finite, there's essentially just three things I have to consider. I have to just plug in 10. So if that works, or if 11 works, or if 12 works, if any of those work, that's going to make the there exists statement true. So when I have a finite domain like this, the there exists statement boils down to just making this or statement. So let's check for these. So when I plug in 10 into my equation, I get 2 times 10 plus 3. Oh, that's 23, and that does not equal 29. If I plug in 11, I get 2 times 11 plus 3, and that gives me 25. So still not equal to 29. Okay, but getting closer. And if I plug in 12, I get 2 times 12 plus 3, which is 27. Oh, that's not equal to 29. Okay, so none of these work. Okay, so does there exist an x such that m of x is true? Well, no, because none of these x values in my domain worked. I could also see that from my or statement, because 10 didn't work, so this was false. 11 didn't work. 12 didn't work. And if every part of an or statement is false, that makes the whole or statement be false. The whole thing is false. Okay, so my there exists x m of x here happens to be false. There was no x in this domain that made this true. So the takeaway when I have a finite domain like this is we can write this there exists statement as a disjunction. And that was just our fancy word for an or statement. Okay. But a lot of the situations that we are going to be dealing with is, well, what if our domain is infinite? Like, so for this example, let's say I had my domain being the integers. Now, for the there exists statement, I'm just asking, is there an integer, maybe multiple integers, just I need at least one, that when I plug it into here, it's going to work. Well, I could solve it, or maybe I could tell, based on the pattern that was emerging here, that there is. X equals 13 makes 2x plus 3 equal 29. It makes that happen. So as a result, does there exist an x such that m of x? Yes, there is. So this is true. this is true. So I will put a t here because there is an x that makes it work.